Right, guys, so this is the first one. 3x minus 2 or 3n minus 2, right? You recognize that, or hopefully you do, as a linear function, right? So this is actually a common problem people have, is understand what it means when it says what happens to the function as n, or x in my case, gets infinitely large. And the problem is because it's a line and you want to focus on the line. But what have I told you about a line? It's an infinite number of points. It's not a line, right? You've got to try and imagine that you could zoom in and see gaps, but because it's infinite, you can't, right? So what we're saying is you can almost pick a starting point, pick, where it crosses the axis. It's not a starting point. There is no starting point, is there? Because it goes on for infinity. But if we said this, if we were to go up a value of x, however far, what happens to the value of y that corresponds to that value of x? It goes up, yeah? So this is an x and y coordinate here, okay? The coordinates are 2/3 and 0. So 2/3 x is 2/3, maps to 0 in y, right? If you go up in the x, and let's go up to 2, come on, stick, 2 and 4. So I've gone up to 2 on the x, and it's gone up to 4. Now, if I keep going up in the x, what happens to the y value? Keeps going up. And you can see that because the line goes up forever, right? So if I said to you, if I make x infinitely large, all right, what happens to y? Y will get infinitely large too, okay? I'm not asking for specific numbers because that's ridiculous when you're talking about infinitely large, right? You're saying, will it be true that if I keep making x bigger, so like when you were little, you went, yeah, I hate you a million times. Well, I hate you a million, or I hate you infinity. Well, I hate you infinity and 1, all right? Well, it's always about going that one more. Infinity is not a number, it's a concept of going on forever. So if I were to carry on forever in my x values and stick a point where the y coordinate matches to it, the y value will just keep going up, yeah? Now in this case, because it's a straight line, it goes up at a constant rate, yeah? That rate is the slope, which we've got as 3, yeah? So every 1 I go up in the x, the y will go up 3 every time, okay? How would you describe the next one? Yeah, so as x gets infinitely large, we don't say infinitely, we say as x gets infinitely large, positive, the y values become infinitely, well, that's the question, is it? Is it small or is it negative? Depends how you want to treat it. So I would say probably say infinitely negative, infinitely large, but negative, yeah? You could argue, but that's not the case, because if we start back here, then it's not negative. But that's not the question. It's if we went infinitely positive in the x values, if that got bigger, what happens to the y? So we're kind of going infinitely off to this direction. And you can see that we will get infinitely negative. Once we've gone over the axis there, it will just carry on getting more and more and more negative, right? But it will be at a constant rate. Right. What about this one? Now, remember to answer the question. Okay. This bit here, look. That's not what we're describing. Okay? It does come down, reach a minimum, go, and we've done that discussion. But as x gets infinitely large, so does y. All right? It will not come back down again, will it? How would we ever know that? Because it's quadratic, and you are now at a level of knowledge that you know what a quadratic does, yeah? We could prove that once we've reached this point, it will never be negative again or getting smaller, but so it's not about this bit, it's not about the bit that is dipping down and go, it's the bit as x carries on going, you know, infinitely large. And that's the bit that we're worried about. Now, does it get constantly large, infinitely large, or is it exponential though? I remember at university I got asked to think about a word though. Is it an exponential increase? No, because it would be an exponential function if it was an exponential increase. It's not, is it? Okay.
Increasing at an increasing rate.
At a quadratic rate, yeah. It's increasing, and that rate is increasing, but it's not exponential. Okay. All right, and it's, by the way, linked to my other favourite topic at the moment. One of the favourite flat Earth things is saying that the planet abides by this 8 inches per square mile or something, and that's what the curve dips off. They use that and say, well, if that was true, you would not be able to sit. And it's like, well, if you actually plot that number and as it drops in that way, 8 inches every square mile, that would give you a parabola, upside down parabola, and that's not a circle, right? That's not what globes are. So it is about how we describe things. We do have to be careful because, you know, people that want to put false information out there will give you a false thing and expect you not to check. So this one does go up. It carries on up infinitely. Here's an interesting one then. Good question. It's a square root. Now the problem is, you are correct in that this actually should go like this. All right? And it would if you had a computer that was clever enough to know that a square root also had a negative value. So what is it? 2x minus 1. There you go. As a computer, when you type in the square root of a number, what does it give you? A positive number. Only ever gives you the positive. This is what annoys me about students when they argue and they put in a test. Oh, but my calculator told me that the square root of 9 is 3. So why should I put 3 and minus 3? Because the calculator says, yes, but the calculator is limited to programming. Your brain is not. So this is what it would look like if you took both. But we're not going to take this side. We're only going to take the top because we're going to describe just one half and say, right, what happens as x gets infinitely large? Does y get infinitely large or not? But does it get infinitely large? This is a difficult one, isn't it? It's just a quadratic on its side. Yes, it does, yes. This will get infinitely large. It's hard to appreciate, hence people that don't agree with big numbers about the speed of planets and things like that. They look at that and they don't believe that that won't stop, but it will. It'll just it will increase at a decreasing rate, won't it? So the increase will get smaller and smaller. But if we went on forever, it would reach as high as we ever needed it to go. It would just take a long time to get there. Okay? So again, this is one that will increase forever. Let's look at the next one. Six times 4 to the power of x minus 1. As x increases, y increases. Will it increase infinitely? Yeah. So as x becomes infinitely large, y also becomes infinitely large. At a what rate? An exponential rate in this case, wouldn't it? This is an exponential. How do I know it's an exponential? Not just because it curves, but because it hasn't, the variable is the exponent, right? But yes, it does have that curved shape. All right, about this next one. This one's an interesting one.
It decreases until it reaches zero.
Yeah. Well, it never reaches.
Till it reaches zero, Jacques?
It never reaches zero.
Never reaches zero. What's it called? What's that line called? An asymptote. So this one, what does y do as x becomes infinitely large? Approaches zero. It becomes infinitely small. Right? And that's the difference. We have to be careful between the word infinitely small and infinitely negative, right? Infinitely large but negative. Because this one does become infinitely small or infinitely closer and closer to zero. So that's an important one. This is the first one that's important, all right? Okay, are you happy with how that, as x gets infinitely large, you can see the graph just gets closer, yeah? Okay, next one. Same thing? Yeah? My scaling just it doesn't look much different, but again, this is one, okay? We'll think about those two. All right. Next one. Same thing again, yeah?
All the zero.
Is this a geometric?
We call it complicated.
So remember, the definition of a geometric is you have a common ratio. Don't have a common ratio, do we? All the way through. This is, I wonder whether you do recognize it as a rational function or a reciprocal function. Right? Did we talk about those? We have talked about it. We talked about the asymptotes and things. So it has one. Okay. And then that was the last one, because this one I was talking about. Okay. Which ones are the geometric? So geometric, this is why I've talked about how we can relate that to different types of functions. So geometric sequences are shown by what type of functions? Exponential, right? So which ones are those? So this is linear. This one's linear. This one's quadratic. This one's not quad, yeah. It's a root. This one, do you recognize it? U1 times R. This one. What about this one? All right, sorry, I don't know. Okay, let's let me just do something. So we're going to talk. We're going to ask the next question, which is about, what was it, the common ratios? Okay, so hopefully now, I did say you could find the common ratio by finding points on the graph and work, but hopefully we don't need to. All right? Why don't we need to? It's in there, isn't it? So what's the formula for a geometric sequence? Okay. So, what's R in this one? What's R in this one? What's R in this one? This needs to be rewritten. Because remember, ratio to the power of n, or n minus 1, not minus n. But we do, using our rules of exponents, have another way of writing to the power of negative x.
Can we do 10 to the power of negative 1, which is 1/10 to the power of x?
Yeah?
That's a common ratio to 1/10.
Exactly. Okay. So there are common ratios. And what do we know about the behavior of those? Well, this one went up. This one went. This one went. So what's the common thing, do you think, about the ones that go down?
Below 1.
So if r is less than 1,
Or greater than
And greater than 0.
greater than 0. Well, this could be negative 5. But that's not what I'm talking about. So r has to be greater than 0. Okay? Because let's have a look at why it's not the r that can be negative, it's the exponent that can be negative. All right? On Desmos, try putting, we've probably talked about this before, try changing one of yours. So I'm going to change this to a negative 4. Okay? If I do it correctly with brackets, you'll notice something. So there's my common ratio 4. There's my common ratio negative 4.
You get 0, 5.
Okay. So just to talk about that briefly. Okay. Let's look at a simple one such as what does it mean to have 2 to the power of x? Well, if we were to draw a table of values, yeah, it'd be 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. Okay? 2 to the power of 0 is 2, 4, 8. Okay. Now, here's what's interesting to me that kind of makes my head spin a little bit. Not just yet. What's in the middle? So 2 to the power of a half. What's that? Root 2. Root 2 is somewhere between 1 and 2, yeah? 1 point something. What's halfway between? So that would be 2 to the power of 3 over 2. So that's the square root of 2 cubed, yeah, so the square root of 8, which is somewhere between, all right? What if I picked a value, could I pick a value between there? Yeah? There's infinite values, yeah? And there'd be lots of points, yeah? So I can fill in all these gaps, absolutely no problem, yeah? All right. Well, here's the thing that makes me go, oh, okay, that's a bit awkward. Well, what if I did negative 2 to the power of x? So, negative 2 to the power of 0, negative 2 to the power of 1, negative 2 to the power of 2, negative 2 to the power of 3, negative 2 to the power of 4. What's the answer? 1? Negative 2, 4, negative 8. No problems. Okay. Negative 2 to the power of a half. Okay. So can't do that. So what about any other points in between? Is that okay? So negative 2 to the power of, give me a fraction between a half and 1. What would that be? So that would be the 4th root of negative 2 to the power of. So that doesn't work either. All right? Negative 2 to the power of 4/5 would be negative 2 to the power of 5. And then the 4th root. How about that? Is that fine? Sorry, negative 2 to the power. Yeah, sorry. 4. And the 5th root. Yeah, sorry. Does that work?
Yes.
That one works. So what we have here, guys, when it's a negative, there are still an infinite number of values that would work, but also an infinite number of values that won't work, which is why we don't get a line. Because remember, a line does not join points together. It is an infinite number of points. So because we don't have that, we can't have our line. So a negative ratio, okay, if I consider all of them, doesn't work. If I just went about plotting these ones, if I limited my domain, so I said x is only an element of integers, like the z value, you remember that? I could plot individual points, but they would have to stay as individual points, which is kind of what Desmos is trying to do, yeah? And not succeeding very well, right? But you definitely can't go and join, because what you'd end up with is a point here and a point up here, and you'd end up with a zigzag line, which again I see because people don't understand what it means, what a line is. They still draw lines with a ruler, joining point. It's not, okay? All right, so what we were then talking about is why are these important, okay? Because the topic we're on is the sum of these series, all right? Okay, so the sum of series is when you add up all the numbers in a sequence. Okay, so if I ask you the question, is it possible to add up an infinite number of numbers where the numbers just keep getting bigger all the time?
Yes, but it would be an infinite sum.
So no, because infinite is not a number. It's a constant, right? It's a way of describing. It's not a value that you can put on anything. So it'd be like me saying, right, what we're going to do is we're going to go up in 2s. Let's do this. We're going to go up, see how far you get before you mess up. We're going to start. I'm going to give you a number. We're going to go up in 2s, but you're going to add on your number. So I'm going to start at 1. So the next number would be 3, but I'm going to add that to make the sum of that and get. Okay, so we're at 4. The next number would be 9. Oh, so now it's, oh, actually that's harder. Because you've got to think what the number would be and what the sum was. Does that make sense? So, so we start at 1. Our sequence would be 1, 2, sorry, what did I say? 1, 3, 5, 7, 9. But so that would be un, but the sum of n would be 1, 3. Yeah, sorry, it should be 4, 6, 8, shouldn't it?
No. 1, 3, 5, 7.
Oh, No, yeah, we already messed up, sorry.
Fail.
So I start 1, we add 2 every time. So 3, 5, 7, 9. The sum of should be 1, 4, 9, 16, 25. So if I asked you to do that mentally in your head and we went around the room, what do you think?
Square numbers.
We get to the next square number.
Yeah.
Get to the highest square number.
Get to the highest square number someone has now.
So, but can you see that if I kept adding all these numbers together, I would just get higher and higher. And if I said, right, once you give me the final answer, you can go to recess.
Be here.
We've got an add up an infinite number of numbers.
That'd be good.
Quite a while.
You can go once we're done. I'm just going to get some coffee. Let me know when you've finished. All right? You'd be like, hang on.
I'm done flying.
Yeah.
Now I'm done.
It's like sending someone to another room and go and ask Mr. Roberts for a long stand. If you go down to the science lab and ask for a long stand, it's what you do when you want to get rid of a naughty child. Because if the other teacher's in on it, they go, oh yeah, just wait there for a step. You come back half an hour later, right, you've had your long stand, on your way back. Right, so we can't add up a certain number. So is there a situation where we could theoretically add up an infinite number of numbers? Not just half. Okay, so what we can do is we can see that in our graphs here, look, this one, remember the red line shows me all the points that I will then add up. So what's happening here? Well, this line, you can already, because of the scale on my screen, it already looks like it's not going down at all, right? So what does that mean? Well, that means the difference from one term to the next term becomes so small that my computer can't recognize it. So it keeps it as a straight line. It is there, but it can't recognize it. So what if I reach a point where I can mathematically add on the next number, but that result is so insignificant, it doesn't make much of a difference? Okay. Could we suggest that actually we've reached a limit to what the value is going to be? Yeah?
Like 9/9 is 0.9
That kind of thing, yeah? So when we've got a situation where the common ratio is between 0 and 1, okay, it gets less and less and less. Therefore, those differences, each term gets smaller and smaller and smaller. So by adding that on, what we'll actually find is there will be a limit to the number that we're reaching, because we'll gradually get to a number. It's kind of like the asymptote thing, but the other way around. Instead of approaching it down to it, we're going to be going up, potentially down to a limit of what we're adding to. Yeah? We know that we're never going to reach that number, but we're going to keep pushing to it. But because that number gets smaller and smaller, we're never going to quite get there. All right? So we'll look at it more next lesson, but just to take this as a kind of summary of it, a kind of introduction, the sum to infinity only happens, we can only do a sum to infinity when we have a situation where the terms of the sequence get smaller and smaller and smaller, and it's not actually a number that we actually get to, but we say we do. It's a limit to what we would eventually get to theoretically. Okay? So the behavior that we're looking for is a geometric sequence that comes down. Why not a linear that comes down?
that has no asymptote.
Okay, so we've already looked, haven't we, at this one. It doesn't get smaller and smaller, it gets more and more. So actually, what will the sum of a linear... Zero. Why? So you'll have an infinite amount of positives and an infinite amount of negatives. And what about the other way, a positive linear? Is it the same thing?
Yeah.
Yeah. So if you were to do it in both directions, but we don't, why don't we have it in both directions? Because when we do a sequence, what's the first term? When n is 1, not when n is negative, right? So that's why we don't consider. So, right, does that make sense in where we're going to be going tomorrow? So we'll look at actually how we do that. Be nice and easy. We've got formula. What can go wrong? Right?
Everything.